So our next speaker is Professor Patrick Totzke from Liverpool, and he will talk about one-dimensional vast languages, universality, pumping, and open problems. So start.
Right, thanks very much. Yeah, so I only realized in retrospect that part of the workshop is an open problem session. So I changed my title back, and this is actually the title of the paper that is has just been accepted at Concours. It's joint work with Scholl, Udi, and Piotrek. And it is about the universality problem, the language universality problem for one-dimensional vector addition systems with states, aka one-counter nets. So let me just begin by dissecting the title. I will be very quick here. One-counter nets. I hope my writing is okay, and I have not the best handwriting. This is the same as one-dimensional vector addition systems with states, and I will pretty much look at it as the presentation in terms of counter automata. So what I have is such a net consists of states. I will write Q. I have transitions. Let me write transitions. T, these are, well, from state to, they read some letter, they have an effect on the counter, and they go to another state. Is that still on the slide? I hope, yeah, okay. Right, and so this means we will have configurations which are simply pairs of a state and a natural number, and the semantics is, well, the vast semantics, right? So you have a configuration P with the counter C can go under the letter A to some configuration, say P prime, and then C plus D, if and only if we have this transition P with the letter D, sorry, P with the letter A with the effect D to P prime in my transition set. So here the sum needs to be non-negative, so it's a vector addition system. Good. So what we want to do now is we want to define languages using these systems, and for that I will pretty much define the language by reaching and accepting a state. So it's the coverability language. So I will define final state, states F. These are subsets of states, and now I define language of a configuration with like L of state, and the counter value is well, consists of those words over some alphabet, such that SC can go under that word to F with any counter value. Right. So all I care about is reaching a final state, and the counter is not important. So this here, of course, is the lifting of this relation to finite words. Right. So now what we know is that due to this acceptance condition and the monotonicity of vector addition systems, we know that the language of a configuration is included in the language of any bigger configuration, C+1. So this is guaranteed by vast monotonicity. And yeah, so now I will perhaps give you a bit of history on the universality problem or some context. So So this is, of course, the problem if a given system for a given configuration, its language is equal to sigma star, so a typical language universality problem from automata theory. And textbook is, of course, that for finite automata, this problem is p-space complete. For one counter nets, we have a result, and for one counter automata, and we know the same thing for push-down automata. So the complexity, or the situation of this problem for finite systems is p-space complete. That's textbook. Similarly, undecidability for push-down automata, non-deterministic push-down automata is similarly, you can find this in the Hopcroft-Ullmann book. For one counter automata, these are push-down automata with a single stack symbol. So this translates into one VAS where you can test the counter for 0. We also know that the language universality problem is undecidable. This is Leslie Valiant in his PhD thesis, 70 something. I want to say 2. And for this model without zero test, one-dimensional vector addition systems with state, the universality problem is Ackermannian, and it's complete. Right. So this problem can be solved essentially by a well quasi-order technique. I won't go into the details. And interestingly, we have a matching lower bound. So now, due to this monotonicity of languages, you can ask the question, well, for a given state in a given system, is there a sufficiently high initial counter value so that you become universal? So the higher you start, the more words does your language contain. And this question that I just mentioned is what we consider. So this is the parameterized intertitle. And the problem that we consider is exactly this, the initial value universality problem. I will write IVU because, as you can see from my slides, I'm relatively lazy. So the problem is this: you're given a one counter net and state. And the question is, does there exist a large enough initial counter value to be universal? So exists N0 with the language of S0 and N0 equal to sigma star. So the sigma, the alphabet is of course part of the input system. So for those of you who are into games, you will know this as the unknown initial credit problem from energy games. And I have just heard that well, one of the Conco reviewers mentioned that the parameterized universality is not perhaps the best name for this, because apparently parameterized problems are normally universally quantified. So this would make the problem a parameterized non-universality problem, but I will stick with this name here. So yeah, I hope the problem is clear. And there's another problem which we call the bounded universality problem. Bounded universality, which I will not go into much more detail here. That's pretty much asking, does there exist a finite number that you can use as a ceiling on the counter, so that you can accept every word in your language without going beyond that ceiling? So if the answer is yes, then of course well, then you have a regular language anyway. But the question is, does there exist a sufficient ceiling so that you become universal? And of course, if you make the allowance higher on the counter, then you get a bigger language. So again, we have this parameterized question. Okay, so these are the questions we consider. And now let me go back here. So the news, so the results from our this Concord paper are that surprisingly, for me at least, these two parameterized questions are undecidable. So both the initial value universality problem and the bounded universality problem are undecidable. So I think this is surprising because intuitively, if you start thinking about this problem, it seems like, well, if your initial counter is big enough, then all that matters is you need to ensure that your counter doesn't drop too much, and there should be some kind of bound on this possible drop. But okay, so I was wrong. This problem is undecidable, and I will show you in a bit the main idea behind this result. And then secondly, we have a bunch of complexity results for decidable subclasses. Decidable subcases. Most interestingly, I think, is the case where you have a single letter alphabet. And we had a small result on unambiguous, ambiguous, and also deterministic on counter. Yes. In fact, yes, the most interesting parts, I think, and that is what the rest of the talk will focus on, is this undecidability result for the initial value problem. And I will give you an idea of kind of a scheme how to decide problems like that, where you have a single letter alphabet. I forgot to say initially, you are welcome to interrupt me any time. You can also tell me to speed up because I don't have a stopwatch on me. Okay, so the first part that I want to show you now is this undecidability result, or at least the main idea. So the initial value universality is undecidable. And so the proof is by reduction from Minsky machine halting. So far, so boring. A bit more concrete, what we will do is we will do the following for some two counter machine, for a two counter Minsky machine. Let's call it M. Construct a one counter automaton, sorry, one counter net. Let's call it A, such that M terminates, halts in exactly n steps, n is a number, if and only if the language of our system, let me write S0 for the initial state, is universal with that counter value n. So that is equal to sigma star. Right. So I won't go into the syntax for Minsky machines, but let me just mention that we assume that such a machine determines a unique run. There's only one possible correct run, and this run is either infinite or it is finite and ends in a halting statement, in which case we look at n, the length of this infinite run. In determining which one of the two it is, if this correct run is infinite or finite, that is an undecidable problem, of course, and that's the problem that we reduce from. Okay, so the main idea here, let me write it like this. The idea is to inspect a run, a potential run, more than once, and every time you read a potential run, you try to find an error, and if it's possible, you're good. If it's not possible, then you have to reduce your counter and start again. That's roughly the idea. So your alphabet will be this is very hand-wavy, but I will write the commands of M. So this says I go from one state to the other and I increment the counter. For example, I can write inc x for this transition increments the counter x. The x, and I also have x greater 0, and I have x equal to 0. These are kind of part of my letters. And I will also use a special divider letter hash. Now, the one counter net will read words like this, a W, which is in fact some starting thing, hash, another subword, sorry, 1, a hash, 2, and so on, until you end some K. And these subwords here may or may not encode a run or a part of a run of this machine. Right. So now what we will do is we will make it so that the system, this one counter net, always starts in a fixed state, a central node, with some budget n that will be in the counter. And you will read the word from the beginning to the end. Every time you read the hash, you make a prediction about what is the potential error in this next word. If your prediction is correct, then you're good to go. You can go back to the central state and start reading the next word. If your prediction is incorrect, you also go to the next word, also in the central state, but you have to strictly reduce your budget. That's the idea. Good. So let me be a bit more concrete. I will let's look at this system here. This doesn't contain everything, but I think it shows it shows the interesting bit. So we start and end every round in this central node here, and this is, I should say, this is also accepting. And now when reading, WI from S0 with budget, sorry, N. Then what we have to do is, upon reading the next sharp, we need to make a prediction what the error in the next word is, and there are 4 cases. The first case is the length of this word is less than I. WI is shorter than our counter. The second thing is WI is garbage, by which I mean it just doesn't follow the structure of the underlying Minsky machine automaton. So this is a regular check. This you can do, and so accordingly, I will just write rec for this contains a regular automaton that detects garbage. In both these cases, what we want to do is accept the remaining subword no matter what. And you see what happens here is if I say, okay, the word is garbage, I go to the state, I detect that it is indeed garbage. If so, I go to some heaven state, and this heaven state allows me to just accept. It's an accepting state, just allows me to loop around, and I will accept. Similarly, if the word is shorter than n, I can just loop here, reduce by 1 at every letter, and eventually at the end of the letter, I will go to the heaven state. So this is possible if my budget is high enough. And the last two possibilities are in fact symmetric. They check they allow us to check cheats on the counter. So here is the case WI uses a letter that says X is equal to 0, when in fact the counter is strictly bigger than 0. And similarly, the fourth case is you claim that the counter is positive, whereas the counter is in fact equal to 0. And in both these cases, what we want to do is return to S0 with a budget which is reduced. Which is at least n, with budget at least n. Yeah. So for example, I predict that there will be a 0 test when in fact the counter is not 0. So I go to the state. I just keep track of my counter here. I ignore everything else. And on a 0 test, I may go back to the initial state. So if in fact this transition will reduce the counter by 1. This means if I was correct and the counter was positive, then I can afford to do that and have at least n. Otherwise, I have to reduce my budget. Yeah. So to deliver the punchline, I will consider two cases to prove that this is correct. Let's say M does not halt. Then it means that, well, there is this unique correct run that doesn't cheat. So I can say there's a prefix of length I, length I prefix without cheating. So now what I claim is if you take this thing and iterate it long enough, you're dead.
There is a typo in the with budget bigger equal to n. Should it be smaller than n?
No, the idea is that if your guess is correct, then you go back to the central state and you haven't lost anything. So if you guess start and you are indeed in one of these situations, that the error, you claim it is 0 where it is not, then your guess was correct. So now you can go back to the central state without having decreased your budget. However, if you guess that you're in one of these cases and it's a correct part of the run, you're not cheating, then the only way you can go back is by using this transition, which reduces your budget. So it should be this way. Okay, yeah. Okay, good. So let me finish the proof. So M doesn't halt, so I have a correct prefix of length n. And now what I say is this word of the form well, I iterate essentially this thing n plus 1 times. I claim this cannot be accepted if I start with counter value n. So the invariant is in fact each round either gets stuck somewhere here or somewhere there, or it comes back to the central state with a strictly reduced budget each round.
So you cannot see what you're writing now. I don't know if it's the case for others. Okay.
Or so this means, is it okay? Can you? The invariant is each round either you get stuck or you decrease the budget, and this means this thing here is not in the language if I start with n. Because I cannot decrease n plus 1 times if I start in n. And the other direction is similarly simple. M halts in n rounds, or it has an accepting halting run of length n. Now, the simple observation is that any word wi that is longer than n, then it means any possible run of my Minsky machine on that word must contain a cheat in at least in the first n steps. Cheats in n steps. So this means I can correctly identify which which error happens on a prefix of length n. So now I can again say invariant of this thing in every round. Every wi is read from S0 with budget at least n, and this means my word is in the language if I start at n. I hope this is readable. Yeah, I know this is technical. I just thought I go through the construction once because these parts are quite simple. Basically, the main idea is you guess the error, and if you guess correct, then you survive another subword, and if you didn't guess correct, you have to strictly reduce your budget. And yeah, apparently this idea has been used on for, I think, undecidability of inclusion for weighted automata. So it comes from this weighted automata world. Right. Are there questions? Otherwise, I would try and squeeze the single letter case into the rest. Okay, I'll just go on. Okay. So the second part, the second thing I wanted to show you is kind of a general proof scheme for, well, the general algorithmic scheme for deciding this initial value problem if I have a single letter only. Yeah, so I will write single letter case. So this means, in fact, well, I have an alphabet of size 1. And now I will identify the words with their paric image. So the question becomes, is the language the whole set of natural numbers? Okay. So now it indeed becomes a question of pumping, hence the alternative title. What we want to do is we want to identify states which allow us to pump, and pumping means you can accept the subword, you can extend the run by some short subrun, and then we can put bounds on this length. So I will we'll just define the crucial thing. The definition is a state, so a control state. Let me call this R. Is pump is a pumping state if it admits a non-negative cycle, which is simple cycle. So a cycle in the control graph which has a non-negative total sum on the edges, so these transition weights, and it's simple, so I don't want to nest this. And so what we can do is we can fix for every state R, we can fix some such cycle, a good cycle. So if R is a pump state, then it has such a cycle, and we can assume it's short and it has all nice properties. So now what we do with this is we define this language, a part of the language, which goes via a pump state. So it's simply words that are accepted by a run that visits this particular control state. it's of course only part of this language. And we will also define this set P, which is simply the union of these pump. Yeah. So this is of course part of the language. Yeah. So the nice observation about this thing is that that if you take away this stuff from the language, so if you take your language and remove everything that can be accepted using visiting a pump state, then this must be finite. Yes, because every time you well, if you want to accept a word that is in this set, then every time you revisit the control state, you must have strictly reduced your counter. Otherwise, this control state would be pump and you would be in P. So this it's not possible to accept infinitely many words in this relative complement here. So this is definitely a finite set. And of course, this means that if you look at the complement of this set P, if it's infinite, then it is a certificate for your language being not universal. That's kind of one of the main ingredients here. So what we want to do is we want to characterize how the set P looks like in order to check if its complement is infinite. If so, your language is not universal. Okay, so now I am going to cheat a bit and look at what I prepared before. Right, so we're looking at these languages here, L, R, and in fact these are simple. These are characterized by short paths. Let me just read the lemma here. So we find a polynomial. It's polynomial in the number of states and our biggest transition weight, such that whenever you have a word which is in that language that visits my pumping state, then it is also accepted by a run of the form a short path to R, a bunch of cycles, and a short path to a final state. So that's pretty much a linear path scheme of a very degenerate form. So short here means that these prefix and suffix are bounded by my polynomial. Yeah? And in fact, the way you do this is you show that if you can cover a configuration, then you can cover it using a word that is in a bounded linear path scheme. So we can kind of replace lots of iterations that repeat stuff in the prefix simply by more iterations of this good cycle. And it's always possible because this cycle is executable no matter what. That's roughly the idea. So the point is that this language here is very simple. It's described by a short prefix, short suffix, and a short cycle. Now, what does it mean for the language itself? And this is a regular language and is accepted by a word of this lasso shape. So the prefix is simply kind of the length. Imagine this the length of alpha and beta together, and the cycle is just my good cycle length. And all I need to do is for which steps I should insert in accepting states. So this language is regular. It's defined by a DFA of bounded size. So the whole size of this whole lasso here is bounded essentially by this polynomial. And I should say that if we are in the unary case, meaning the encoding, so this factor here is 1, then we can even create such an automata description in polynomial time, essentially. However, if this factor is exponential, because you have binary encodings, then this might be bigger. Good. Now, first, the last thing I want to say is, well, if you look at this union P, remember we want to check if its complement is infinite. you can describe it as, well, as the union of such lassos. So you can essentially write it down as a NFA, which has this lollipop form. Yeah, it's the shared prefix here. And these are the cycles corresponding to my languages for different R's, and there are not too many of those. Yeah. And also this means I can, in fact, take the product of all of these here and get an automaton of this lasso shape for the language P. But of course, the length of this cycle bit in that language for P will be the product of all possible cycles here, which could be large, because these could be of prime number length. Yeah. Bottom line is, if you want to check if its complement is infinite, all you need to do is you need to find a word which is long enough to be in the cycle part, and it is not accepted. And of course, if there is such a word, then there's the shortest such word, and this shortest word will not be going through this cycle more than once. Yeah. So this gives us a check for whether this complement of the language P is infinite, and all of this is effective. Good. So now, let me deliver the punchline for universality. I will just drop this on you. A characterization. There is poly B such that the language of a configuration, so notice this is just universality, is not everything if and only if one of two cases. Either you find a short witness for non-universality, and short meaning less than B. So let me N shorter than B, which is not in the language. Clearly, this witness is non-universality. And the second case is you witness that the complement of P is infinite. So this means there exists an N, which is not in P, and well, you're bounded by this prefix B from below, and by the prefix B to the power of states, because that bounds my product from above. Right. Now the question, so this is for universality, and there's a very similar characterization for the initial value universality problem. So basically, initial value universality, there exists such a number which is sufficient for a universality if and only if first your complement is finite of P, and secondly, your underlying automaton must be universal. Right. So I hope this is intuitive why these are necessary and sufficient. Now let me just mention that for checking all of these things, so now it becomes a question: how costly are those checks? So, for example, if your encoding of the net is unary, then checking if a word is bounded polynomially, because in this case you're polynomial, is in the language, can just be done by forward exploration. So that's kind of cheap. If you want to check if this condition holds, what you can do is you can guess your word n in binary, because it's now exponentially bounded. And in order to check if it's in P, you just need to check if it's in in one of these languages here, and this is possible by repeated squaring. So I think I should wrap up. Let me just mention, since this is filling a table, here's your table. This summarizes all these little results that we have, and some of them are completeness results, some of them are not. So let me just point out what I've shown you is the undecidability for the initial value problem. It's here and there in arbitrary alphabets. And what I also showed you is the an approach that we get for a single letter alphabet, non-deterministic automata in unary and binary. This is this and that result. So the extra complexities come from estimating the cost of these individual checks. Okay, I hope that's okay. I think that's all from me for now, and I am on time. Fantastic. Igor Popatov has asked me to advise, advertise reachability problems. So if you have something lying around, send it to RP. The deadline is, I think, the 17th this month. Okay, thank you.
Thanks, Patrick, for the very nice presentation. And if there are any questions, then please ask them. Okay. Seems there are no questions.
Okay. Well, you can take it offline, ping me afterwards.
Yes. So, yeah, thanks again.